Hi, welcome back everybody. In this video I'm going over problem number 1 from the 2014 AP Physics C Electricity and Magnetism AP exam. In this problem you had a setup where you had two resistors in series that themselves were in parallel with a third resistor of unknown value. And there was an ammeter measuring the current coming out of the power supply and a variable power supply. So part A of this problem was simply to have students plot the data points as a function of potential difference and draw a straight line that best represents the data. So there are a few things to note about this plot. First of all, you needed to label your horizontal and vertical axes both with the quantity, in this case current and potential difference, and also the units for that quantity. So I labeled the units in parentheses, and I converted the currents into SI units, so I plotted the current in amps. Now, in drawing the straight line, notice that the straight line is supposed to fairly well represent the data. In this case, it probably would have been a little bit disingenuous to have the straight line going through the origin, because I think that in this case, going through the origin would not represent these data all that well. If you ended up doing that, it would end up skewing things a little bit. And also, I have circled a couple of points on this line that are not actually data points. That's going to be for part B, recognizing part B is coming up where I'm going to have to calculate an equivalent resistance. So we have our straight line. We have points falling on roughly equal parts of that line, and we're ready to move on. So in part B, calculate the total resistance of the three resistor combination in this situation. So we have Ohm's law telling us that the delta V for the power supply is equal to the current coming out of the power supply times the equivalent resistance. I don't like this term total resistance because that just implies that you could add up all three resistors, which is definitely not what they're looking for here. Equivalent resistance is a much better term, but in any case, we recognize that the current, which we're plotting on our vertical axis, is equal to the potential difference of our power supply times 1 over the equivalent resistance. The reason we wrote it this way is because now we have this in the form dependent variable equals independent variable times slope, recognizing that in this case our slope is 1 over the equivalent resistance, the slope of our plot, that is, the slope of our best fit line. So therefore, the equivalent resistance must be 1 over the slope. And the slope is, in this case, is given by change in vertical over change in horizontal, that is rise over run. So that's I2 minus I1 all over V2 minus V1. So in order to plug in quantities for I1, I2, V1, and V2, we need to pick 2 points. Well, those are the points that I circled earlier, the points that are easy to identify from our best fit line as it is going through, as it's representing our data points. So we have our 2 points, and we plug in our 2 points into that slope formula that we have. And when we do that, we get 0.12 divided by 8.4. So what we're trying to get out of this is recognize that the equivalent resistance is 1 divided by the slope. Well, that's convenient. 84 is 12 times 7, so just shifting a decimal place over, we realize that our equivalent resistance here is 70 ohms. So going back to see where the points have been allotted so far, in part A, that was worth 3 points. They gave 1 point for labeling both axes with proper variables and units and using appropriate linear scales for both axes. In other words, if you missed any of those, you wouldn't have gotten that point. Now, appropriate linear scales, we mean essentially that your graph is taking up most of the provided space in both directions. So, say labeling the horizontal axis going from 0 to 20 or 0 to 30, that would have been bad. Or labeling the vertical axis going from 0 to 0.4, that would have also been bad. That sort of thing. Second point was awarded for properly plotting the data points. If you know how to plot, you got that point. Third point was awarded for drawing a reasonable best fit straight line. And that in particular is quite important. Their best fit straight line actually ended up going through the origin, so I guess it was okay for having your best fit line going through the origin, though the origin was not one of the points that they ended up using for calculating their slope. Now going on to part B, they gave 1 point for calculating a slope using points on the line drawn in part A as opposed to data points. So you should not use data points unless those data points clearly fall on your line of best fit. So if you just plug in a couple of data points, you're not going to get that point. 1 point was given for correctly relating the slope to the resistance, which is what we did up here. It's the inverse of the resistance. And 1 point was given for the answer with correct units. They got 61 ohms with their calculation. Then they also noted that linear regression would yield 64 ohms. So I would guess that this is within the margin that they would accept on this type of thing, our result of 70 ohms. Now, moving on to part C. Calculate the value of R1. Well, we calculated the equivalent resistance, and we note that R1 is in parallel with our other two resistors, which themselves are in series with each other. So, setting up a formula for equivalent resistance, we have 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus R3, and then we plug in our values after writing our givens. So, the result of this ends up, in fact, we isolate for 1 over R1 first and then plug in our values. And upon doing that, we find that R1 is about 230 ohms using the numbers that we had. How are the points distributed here? There were 2 points for this part. 1 point was for substituting the answer from part B into a correct equation to solve for R1. And 1 point was given for recognizing that R2 and R3 are in series. So that's essentially what was given right here for that second point, and then right here for our first point. Moving on to part D, the power supply is now fixed at 12 volts. Upon doing that, calculate the current through R2. Well, let's see. The path that has R2 in it has an equivalent resistance of 100 ohms. So we can take a Kirchhoff's loop rule and recognize the voltage of the power supply minus the current going through the right side times the equivalent resistance of the right side is 0. But the equivalent resistance of the right side is just R2 plus R3, which we already got. That's 100 ohms. So what we're left with is 12 volts divided by 100 ohms gives you 0.12 amps. So 2 points were given for this part. 1 point for using a correct equation to solve for I2. That's what we have right here. And 1 point for the correct answer with units. No units, no credit. Part E. Resistor 3 is now removed and replaced by an open switch in series with an uncharged 4 nanofarad capacitor as shown here. The power supply is still fixed at 12 volts. Calculate the current in R2 immediately after the switch is closed. Well, what's the deal immediately after the switch is closed and you have an uncharged capacitor? That capacitor is not providing any voltage potential difference, which means that it's like a wire. So immediately after the switch is closed, we basically just have current going only through that 50 ohm resistor on that side. And again, that 50 ohm resistor is in parallel with R1, so we can just make a nice little loop. We have our loop rule telling us the power supply voltage minus I2R2, where R2 is that 50 ohm resistor, minus the potential difference across the capacitor is 0. And since delta V initially at the instant the switch is closed is 0, that means that I2 is just V over R2, and we get 0.24 amps there. So the points on part E were awarded. There was just 1 point there for substituting proper values into a correct expression to solve for I2, that current. So there were no points for the answer in this particular part. Now, I should note something, that you should be prepared to solve for I of t if necessary by noting that this delta V and say it's like, okay, definition of capacitance is charge per unit voltage, and then take a time derivative so you'll get a dIdt there, that sort of thing. So just be prepared for the potential to have to do such a thing. Now, Part 2 of Part E says that the 4 nanofarad capacitor, so the switch is removed. So a long time after the switch is closed, will the magnitude of the current in R2 be greater than, less than, or equal to the magnitude of the current through R2 found in part D? Well, this one is actually very straightforward. A long time after the switch is closed, the capacitor is fully charged, which means that there is a 12-volt potential difference across that capacitor and no current is going through that section. So less than, because after all 0 is less than that 0.24 amps that we got in, or that 0.12 amps that we got in part D. So justification, long time after the switch is closed, charge will build up on the capacitor until no more current goes into that branch and I2 goes to 0. So you can also think of this as saying that ddt of the charge on the capacitor goes to 0, which means that the current going to the right side is 0. So I2 must therefore be 0. Now, part F replaces the 4 nanofarad capacitor with an uncharged 10 nanofarad capacitor. Will the current in R2 immediately after the switch is closed be greater than, less than, or equal to the current in part 1 of part E? Well, replacing that 4 nanofarad capacitor with a 10 nanofarad capacitor does absolutely nothing in terms of what happens initially after the switch is closed. It slows down the rate at which that capacitor is going to get fully charged, but in the end, we're just dealing with the same situation at the instant that the switch is closed. In other words, it's still going to act like a wire. So that's what we have there. The way the points were distributed, part 2 of part E, kind of going back here, they gave 1 point for selecting less than and 1 point for a correct justification. The example they gave was after a long time the capacitor is completely charged and there is no current in the capacitor branch because the voltage across the capacitor is equal to the battery voltage, so there's no current through or voltage drop across R2. And they also noted that if the wrong choice was selected, no credit was given for that part at all. Very brutal there. So in part F, the credit was given such that you got 2 points there. And 1 point was given for selecting equal to, and 1 point was given again for the correct justification, saying that immediately after the switch is closed, the uncharged capacitor has no resistance, so it acts like a wire, therefore it does not affect the current going through R2. And they mentioned that the mathematical calculation in part 1 of part E, does not depend on the value of C, so changing the capacitance has no effect. That's also an acceptable explanation. And again, no credit was earned if you chose the wrong choice. So a lot of times these pick a greater than, less than, equal to and justify your answer. These are often all or nothing. So keep that in mind. So that is the end of our solution for problem number 1 on the 2014 AP Physics C, E&M exam. Now, some things that the chief reader mentioned in the student performance question and answer for this problem. In terms of the intent of the question, this question involved an experiment where voltage was varied and current was measured. In addition to assessing data analysis, the question was intended to assess student understanding of RC circuits, especially the loop rule. It required students to use data to make a graph of current versus voltage to determine resistance, to solve a few simple loop rule questions, and then to answer and justify questions about capacitor charging behavior. And how well students performed, the average score on this was 9.78 out of 15 points. So that is quite a high average score. Common student errors or omissions. Most student errors came from not using the graph appropriately to determine the effective resistance. Because the question asked explicitly for current versus voltage rather than more usual voltage versus current, many students made the inverse graph and did not recognize that. So be careful what they're asking. Students did not use the slope of the best fit line in some cases, but rather used the data points provided to calculate the slope. Again, you did not get that point if you did that. And another common error was students were not able to justify their responses by explaining the underlying physics. And then the chief reader mentioned, based on experience of student responses, what message would they like to send to teachers that might help them to improve student performance? 1. Students need to understand the purpose of a best fit line and need to understand the slope of the line is the meaningful quantity rather than the slope between two arbitrary data points. 2, students should be able to graph correctly, including labeling and scaling axes, and understand how to make theoretical predictions from graphs. They have been getting more and more into that sort of thing lately with all of the AP Physics classes, not just AP Physics 1, but also the AP Physics C classes and those exams as well. And 3, students need significant practice constructing airtight justifications that include skillfully worded connections to the basic physics. Too many students seemed to feel that restating the fact already provided in the question using other words was equivalent to a justification. That is not equivalent to a justification. That is called circular reasoning, and that is fallacious logic, and you would get no points for that. So that was the commentary given based on student responses, and if you have any questions on this problem in general, please note them in the comments section. Thank you for watching.